please subscribe to support the channel. What might be hiding in the deepest parts of space, far beyond the reach of our eyes, where even light disappears into absolute darkness? Scientists have discovered regions so powerful that nothing escapes them. Not planets, not stars, not even light itself. And these strange cosmic traps are called black holes. They bend space, twist time, and swallow anything that gets too close. Yet they sit out there silently as if guarding the universe's greatest secrets. But before we can face one of these monsters, we have to take the very first step of our journey, lifting off from our home world. And as we fire up the engines and begin climbing toward the dark, a new question rises with us. What does Earth look like as we leave it behind and rise beyond the blue sky? What does Earth really look like once we rise beyond the blue sky? Once we climb high enough that the clouds fall away beneath us, and the world stops feeling like a place and starts feeling like a memory. As the engines roar and the spacecraft surges upward, the ground slips away faster than our eyes can track. Streets turn into tiny glowing threads. Cities blur into sparkling clusters. The coastlines we know stretch into soft curves, and the continents begin looking less like land and more like shapes drawn onto a giant map. Every second we climb, everything familiar gets smaller, quieter, and more unreal, as though we're leaving all of human history behind with the simple push of an engine. Higher still, the oceans, those massive bodies of water that once felt endless, start shrinking into calm blue patches. Clouds drift beneath us like slow cushions of white, and storms that once seemed violent from the ground now look like swirling, harmless spirals. Even the tallest mountains flatten into gentle wrinkles on the planet's surface. We're rising faster than any plane has ever flown, breaking past the limits of our sky, and the speed itself feels like it's pulling us away from the world we know. The sky darkens into a deeper and deeper shade of midnight, and the curved edge of Earth begins to show, glowing lightly as sunlight bends around it. Then comes the reveal. Earth, our home, the entire world of oceans, forests, deserts, cities, and people, becomes nothing more than a glowing marble drifting in the blackness. Blue, white, and faintly golden, wrapped in a thin shell of atmosphere that suddenly looks incredibly fragile, unbelievably small compared to everything around it. This is the first time we see our planet the way space sees it. Tiny, delicate, floating alone in a huge cosmic sea. And it's beautiful, but also humbling. Because the darkness ahead of us stretches wider than anything we can imagine. Out there, past that soft glow, are objects stranger, heavier, and far more mysterious than any landscape on Earth. And somewhere in that darkness, hidden between distant stars, something is waiting for us, something twisting space itself. As we leave our world behind and drift fully into vacuum, one question silently pulls us forward. If Earth looks this small from here, what secrets does the quiet of space hold as we go deeper? What does true silence actually sound like? Not the quiet of a bedroom at night, not the pause between two heartbeats, not the soft hush before a storm. Those are all filled with tiny noises we don't notice until we go listening for them. But out here, As the last layers of Earth's atmosphere fall away behind us, we reach a kind of silence that human ears were never meant to experience. A silence so complete, it feels like the universe itself is holding its breath. There's no air out here, no air to carry sound, so nothing can echo, nothing can whisper, nothing can even hum unless it's inside our ship. It's the closest thing to absolute silence that exists, and it surrounds us like an enormous, invisible ocean stretching in every direction. As we drift deeper into this quiet, the tension becomes almost physical. Back on Earth, even in the calmest moment, there were always little reminders that life was happening around us. Wind brushing past buildings, leaves rustling, birds calling, cars moving, people talking. Even in the stillest night, there was always the soft pulse of the world. But here, the silence is so perfect that our own breathing suddenly sounds loud. Every small click of a control panel feels sharp. The gentle vibration of the engines becomes a constant reminder that the spacecraft is the last bubble of noise we have left. And outside that thin hull, nothing. Not a whisper, not a murmur, not even the faintest tremble of sound. If you could step out without protection, your ears wouldn't hear silence. They'd hear nothingness, because there's simply no sound to hear. Inside the craft, the hum of electronics, the faint buzz of power systems, and the soft whir of air recyclers become the soundtrack of our journey. These tiny mechanical noises, which once seemed ordinary, now feel like lifelines, proof that something is still moving, still functioning, still alive inside this vast, silent vacuum. Space doesn't roar. It doesn't sigh. It doesn't warn. It just exists around us, calm and cold and empty, making our spacecraft feel like the only living thing for light years. And in that deep, heavy quiet, our senses shift. Our eyes take over. Because if space has no sound, it certainly makes up for what we see. As we look forward through the main window, faint specks begin to appear. Just a few at first, scattered like grains of dust on a dark floor. But as our eyes adjust to the blackness, those specks multiply. Hundreds, thousands, millions of tiny glowing points scattered across the endless dark. These aren't sparks or illusions, they're full suns, each one burning with its own light, its own planets, its own mysteries. They flicker lightly, twisted by distance and by the thin glass between us and the vacuum, and they form a thick, shimmering blanket that seems to wrap around the entire sky. And this is only the beginning. Those faint lights ahead, we're not just looking at them, we're heading toward them, right into the crowded starfields of our galaxy. Every one of those distant specks is a giant furnace of nuclear fire, and soon we'll be moving between them, weaving through the Milky Way like a tiny ship in an ocean of suns. But hidden in that ocean, somewhere among those glittering lights, is something far heavier and far stranger than any star. Something we can't see yet, but whose presence is already bending the space around it. Which leads us to the next question, pulling us forward into the dark. What are those bright, flickering lights waiting for us deeper in the starfields? And what secret monster hides among them? What are those bright, flickering lights scattered across the darkness ahead? Those tiny pinpoints that seem to shimmer as if they're signaling to us. At first glance, they look small, almost delicate, like someone sprinkled glowing dust over a black canvas. But as our ship flies deeper into space, those flickering specks multiply, crowding together until the darkness between them becomes thin, stretched, almost fragile. It feels as though we're sailing toward a cosmic shoreline made of glittering sparks, and each one pulses with a silent rhythm that pulls us forward. But the mystery remains. What exactly are we flying into? The tension builds as we get closer. Those little lights, so harmless looking from a distance, are anything but small. Each one is a massive burning sun, millions of times larger than Earth, hotter than we can imagine, and powerful enough to tear planets apart if they wander too close. Out here, in the vacuum of space, their brightness lies to us. They appear tiny only because they're unimaginably far away. But as we approach the star fields of our galaxy, the truth becomes obvious. We're entering a region where stars are packed so densely that space feels alive with glowing fire. Some stars pulse, some flare, some drift in pairs or triplets, orbiting each other like celestial dancers. And all of them burn with ancient energy, older than Earth, older than our species, older than everything we've ever known. Now the reveal hits us full force. Our journey isn't just skimming past a few lonely stars. We're diving straight into the Milky Way's thickest star clouds, a glowing river of light made from billions of suns, all drifting through space together. These clouds aren't made of water or air. They're made of pure starlight and dust, swirling through a vast spiral galaxy that stretches 100,000 light-years across. We're flying through regions where stars form, where planets are born, where nebulae glow like cosmic storms frozen in time. The view's overwhelming, light everywhere, color everywhere, a whole sky bursting with suns. It feels like we stepped into a living painting, one that shifts and breathes with every passing moment. But hidden in this beautiful chaos, tucked between these glowing giants, lies something far more dangerous than any star. We can't see it yet, not directly. Black holes never announce themselves with light. They hide, waiting, bending the space around them like invisible whirlpools. And somewhere in these star fields, somewhere among the golden sparks and crimson giants and pale blue dwarfs, is the very monster we're searching for. And that brings us to the question hanging over our path like a shadow. How do we find the black hole and all this blinding starlight, especially when we can't see it at all? How do we know where a black hole is if we can't actually see it? Out here in the middle of the galaxy, surrounded by blazing stars and drifting dust clouds, the very thing we're searching for is completely invisible. It doesn't shine, it doesn't glow, it doesn't reflect light, it doesn't give us even the faintest glitter to follow. A black hole hides by swallowing all the light around it, turning itself into a dark patch carved out of the universe. And as our ship travels deeper into this crowded region of space, it becomes clear that finding something that gives off no light at all is like trying to spot a hole in an endless night sky, night inside of night. The tension climbs as we realize the problem our instruments face. Telescopes, sensors, cameras, none of them can catch direct sight of a black hole, because there is no sight to catch. A black hole doesn't behave like a star or a planet. It doesn't glow like a nebula or reflect light like a moon. Instead, it hides behind its own gravity, bending the very fabric of space so intensely that any light near it gets dragged inward and trapped. It's like hunting a ghost in the middle of a fireworks show. Everything else is blindingly bright, while the ghost leaves no shadow, no sparkle, no warning. The only thing we know for sure is that somewhere near us, space is being warped by an invisible monster. And then the reveal snaps into focus. Even though black holes give off no light, they can't hide their influence. Scientists discovered that the best way to find one is to ignore the darkness and watch the stars instead. Out here, some stars move normally, slow, steady, predictable. But others behave strangely. Some loop around in tight circles. Some swing suddenly as if yanked by something enormous. Some accelerate for no reason and then drift as if nothing happened. It's like watching a crowd of dancers suddenly pulled off balance by invisible hands. These odd motions are clues, signs that something powerful is pulling on them, something massive yet unseen. This is the invisible map our journey follows, not a map made of landmarks or bright lights, but a map made by the paths of stars wobbling around an invisible center. When a star's orbit bends sharply or whips around too fast, scientists take notice. These motions trace out the shape of the gravity well tugging on them, and the moment we find the place where star after star is being dragged into tight and furious loops, where their paths all angle toward the same empty spot, that's when we know we found our target. Ahead of us, not far now, we can see that strange region, a cluster of stars moving in spirals, spinning faster than stars should ever spin, almost as if something monstrous is coiling in the dark center. Something we can't see, but absolutely feel in the motions around it. And that leads us to the next mystery waiting in the swirling distance. Why does one particular star move in such a strange looping dance, as if something huge is yanking it around? Why does one star ahead of us appear to dance in such a strange looping pattern, twisting and curving through space like it's caught in some cosmic choreography no other star is following? At first glance, it looks almost playful, darting around with sharp turns and sudden accelerations, as though it's performing a wild routine all on its own. But there's nothing playful about the forces acting on it. This star's motions break every rule we expect from normal orbits. It isn't drifting calmly the way stars usually do. It's whipping around in tight, rapid arcs that should be impossible for something so massive and so far from any visible companion. Something is tugging at it from the darkness, something powerful enough to bend its entire path like a puppet on a string. The orbits tighten and then stretch, looping back on itself in a motion that suggests it's under extreme gravitational stress. The star's path is so fast that it completes a full loop in a fraction of the time a normal star would need. As if some unseen giant has grabbed it and it's whipping it around with incredible force. The loops aren't smooth, they're sharp, intense, almost frantic. Every twist in its path screams that something enormous and invisible sits inside that dark center. And here comes the reveal, the truth that scientists eventually uncovered. The only thing that could force a star into such a wild orbit is a massive black hole. Not just any black hole, but 1 millions of times heavier than our sun. This invisible monster is pulling on the star with such overwhelming gravity that the star has no choice but to race around it at incredible speed. The dance we're seeing isn't a dance at all, it's survival. The star is trapped in the grip of a black hole so dense, so powerful, that even a huge burning sun becomes nothing more than a glowing bead being flung around in circles. This violent orbit is the star's way of staying alive, because slowing down or drifting slightly closer would mean falling toward the point of no return. But now that we spotted this one frantic star, a new question rises in front of us, colder and darker than the space around it. Because if the black hole can yank a star around like that, if it can force a sun into a desperate loop, then what happens when a star gets too close? What happens when gravity becomes so strong that even a star, a giant furnace of nuclear fire, can't hold itself together? What would we witness if a star wandered just a little too near this cosmic monster? What happens when a star wanders too close to a black hole, close enough that not even its immense heat or pressure can protect it? As our spacecraft glides closer to the swirling region, we see one such star drifting near the danger zone. At first, it looks perfectly normal, glowing softly, drifting calmly as stars do. But then something changes. Its surface begins to ripple. Its round shape stretches ever so slightly, like a ball of molten metal being pulled from one side. The star starts to elongate, slowly at first, then faster, as though invisible hands are grabbing opposite ends and pulling with steadily growing power. And this is where the mystery reveals itself in the cruelest way. What force in the universe could possibly distort a star, a massive sphere of burning plasma, as if it were made of liquid? The tension tightens as we watch the scene unfold. The star's far side is tugged gently, but its near side, the side facing a black hole, is pulled with terrifying strength. This difference in gravitational pull is extreme and violent. Scientists call it tidal force, the same kind that moved the oceans on Earth, but multiplied by millions. On Earth, tides shift water. Near a black hole, tides rip stars apart. The closer the star drifts, the more its body stretches. It bulges toward the black hole, its surface peeling away like strands of glowing taffy. Shockwaves ripple across its outer layers. Huge loops of plasma snap off and spiral into the void. It's the kind of destruction that happens silently in space, but visually, it's like watching a giant being slowly unmade by an invisible predator. And now the reveal hits with full force. The star is no longer a sphere. It becomes a long, bright ribbon of gas, drawn thin as it spirals inward toward the black hole's maw. This thin, glowing strand is called a tidal disruption stream, and it's one of the most violent events in the universe. The black hole isn't just pulling on the star, it's unraveling it, piece by piece, stretching it into a long, twisting river of plasma that wraps around the darkness like a fiery serpent. Eventually, parts of that stream will join the swirling accretion disk around the black hole, heating up to unimaginable temperatures, glowing brighter than entire galaxies for a brief moment before being consumed forever. The star's life ends not with an explosion, but with a long, slow, terrifying stretch into nothingness. But as we watch this destruction, as we see a star, something millions of times larger than our ship, being torn apart like soft dough, a new thought rises from the deep dark inside the cockpit. If a star can be stretched, twisted, shredded by the gravity of a black hole, then what about something far smaller, something fragile, something built of metal walls, wires, oxygen tanks, and human bodies? Because if this is what happens to a star that gets too close, we have to ask ourselves, what warning signs will we encounter as we approach the black hole's danger zone? And will we even recognize them before it's too late? What signals warn us that we're getting close to a black hole's danger zone? Close enough that the universe itself begins to behave strangely. As our ship continues forward, leaving behind the shredded remains of the star we just watched unravel, the space around us starts to feel different. Nothing jumps out at first. There's no alarm, no sudden flash, no cosmic sign saying turn back now. Instead, the warning signs creep in slowly, almost politely, like the universe is giving one last quiet chance to stop before things get truly strange. But if we pay attention, we notice them. Subtle shifts in the starlight, strange flickers in the darkness, invisible hazards rising around us, as if space is whispering that we're crossing a boundary humanity was never meant to approach. The tension rises when the first measurable change appears. Radiation increases. The ship's sensors begin to twitch, picking up particles moving at incredible speeds. Cosmic rays, X-rays, and gamma rays, energies high enough to shred DNA and fry electronics, begin flooding the region as matter falling toward the black hole heats up to extreme temperatures. Our shielding holds, but the readings spike higher than anything we've seen before. Then we notice something even stranger. Light from distant stars no longer looks straight. It bends, curves, and twists as if it's bending around something invisible. Every direction we look, the cosmos appears slightly distorted, like we're peering through a thick lens of warped glass. The nearer we get, the more intense the bending becomes, until some stars seem to stretch or doubled, while others shimmer in impossible ways. And now comes the reveal behind this eerie distortion: gravitational lensing. The black hole's gravity is so strong that it doesn't just pull in matter, it bends the path of light itself. Light normally travels in straight lines, but near a black hole, those lines curve like ribbons cut in a whirlpool. The black hole doesn't glow, but the space around it shines with twisted reflections of the universe. Distant stars appear in places they shouldn't be. Some look like they're smearing across the sky. Space is literally being stretched and bent in front of our eyes. This isn't an illusion. This is physics breaking into forms we can see. Gravity painting invisible structures onto the sky like cosmic brushstrokes. But even more unsettling is the feeling that these distortions are just the beginning. Because the deeper we go, the more the bending intensifies. Stars blur into arcs, light folds over itself. The boundary between out there and right here becomes uncertain. Our eyes, which have guided us our whole lives, begin to lose their trustworthiness. And soon, the warping will grow so extreme that even the shapes of stars, the glowing rings of matter, and the lines of our own ship might appear wrong. And that brings us to the next unsettling mystery, waiting just beyond this region of bending starlight. Why do the stars ahead start to look smeared and stretched, as if space is twisting them into strange shapes right before we reach the black hole's glowing ring? What signals warn us that we're getting dangerously close to a black hole, close enough that the universe itself starts behaving in ways that feel wrong to the human eye? At first, everything around our ship still looks normal. Stars glitter in every direction, darkness stretches endlessly, and space feels like the same quiet ocean we've been drifting through. But then, tiny clues begin slipping into our view, almost too subtle to notice, like the universe is testing whether we're paying attention. A strange flicker here, a faint shift there, and suddenly the question becomes impossible to ignore. What exactly is happening to the space around us? The tension arises when our instruments begin detecting a slow but steady spike in radiation. Not the gentle background radiation that fills all of space. This is sharper, stronger, more dangerous. The kind produced when matter near a black hole heats up to unbelievable temperatures. X-rays and gamma rays, the universe's most energetic and deadly forms of light, begin streaming across our path. Our shielding groans as it absorbs the spikes, and alarms flash briefly across the control panels. If we were unprotected, this invisible storm would be enough to tear apart our cells in seconds. Then the visual warnings begin. At first, the stars ahead look a little off. Some appear slightly curved, almost like someone tugged at their edges. Then others smear into thin streaks, stretching across the darkness as if space is pulling on their images. It's not the stars that are broken, it's the space between us and them. Light, which normally travels in perfectly straight lines, is now bending, twisting, curling around something massive that we can't see directly. The black hole's gravity is so intense that it warps the fabric of space like a heavy weight pressing into a trampoline. And the path of every photon, every particle of light, bends as it passes through this distorted region. And now comes the reveal. This is gravitational lensing, one of the strangest and most beautiful effects in the cosmos. The black hole acts like an invisible magnifying glass, bending and stretching the light of distant stars around it. Some stars appear doubled, some appear in arcs, some form thin glowing rings. The black hole itself stays hidden, but the space around it reveals its presence by literally twisting reality. Light becomes a paintbrush, and gravity becomes the artist, smearing the universe into new shapes. But here's the unsettling part. The warping has only just begun. The deeper we fly into this region, the more extreme these distortions will become. Soon, the stars won't just look curved. They'll look melted, stretched, or folded around an unseen center. Our sense of direction will blur. Our eyes will struggle to recognize what's real. Space is warning us, not through sound or color, but by twisting everything we see. And that leads to the haunting next question pulling us forward. If the stars already look smeared and stretched, what will we see when we reach the edge of the black hole's blazing, spinning ring of fire? Why do the stars ahead of us start to look smeared, stretched, and warped, almost as if someone dragged their light across the sky with a cosmic paintbrush? At first, it seems like a trick of our eyes, maybe a glitch in the ship's display. But even when we switch to backup systems and optical sensors, the distortion stays. Stars that should appear as single, sharp points now stretch into thin glowing arcs. Others ripple like reflections in disturbed water. Some seem to split into two, drifting apart and coming together again. This isn't normal. This isn't optical error. This is the last clear view of the universe behaving the way we expect it to. The tension tightens as the distortion grows stronger with every kilometer we travel. The black hole's gravity is no longer a distant influence. It's shaping everything we see. Space itself is bending under the weight of its immense pull, and starlight has no choice but to follow those bends. Imagine a mirror that curves, bulges, twists, and sinks all at once, turning your reflection into something unrecognizable. That's what the black hole is doing to the universe around it. The stars aren't actually melting or stretching, but the paths their light takes to reach our ship are being bent and twisted by warped space. It's like watching the cosmos through a funhouse mirror built by gravity. A mirror so powerful that even the speed of light can't escape its pull. Every star we see becomes a distorted version of itself, wrapped around an invisible center we haven't yet laid eyes on. And now the reveal unfolds in dramatic fashion. This bizarre visual chaos means we've reached the region near the accretion disk, the glowing, swirling ring of superheated gas and dust spiraling into the black hole. This is the final boundary before things become truly extreme. The accretion disk is where matter heats up to millions of degrees as it races around the black hole at nearly the speed of light. Its brightness can outshine entire galaxies. Its spinning motion creates deadly radiation storms, and its presence tells us that the black hole isn't just nearby. It's close, very close. We're witnessing the last normal starlight before the black hole's influence dominates every inch of space ahead. The stars look smeared because their light is being dragged across our vision by the warped space near this colossal structure. The closer we get, the more the disk's blazing glow overpowers the sky. Soon, those distorted stars will fade into the background, replaced by the blinding, swirling fire of the accretion disk itself. And that brings us to the next burning question in our journey. What exactly is this spinning ring of fire surrounding the black hole, and why does it glow so fiercely in the darkness? Why is the black hole surrounded by a glowing ring, one so bright it outshines entire galaxies, even though the black hole itself gives off no light at all? As we move closer, that ring comes into full view, swirling like a blazing halo wrapped around pure darkness. It twists, churns, flares, and ripples with violent bursts of energy. It almost looks alive, but this light isn't coming from the black hole. It's coming from the material racing towards it, material that's being shredded, stretched, and heated beyond imagination as it spirals inward.
The tension builds as our ship drifts toward the edges of that violent whirlpool. Gas, dust, shattered fragments of stars, and even entire planets, anything unlucky enough to wander too close, get caught in the black hole's gravity. They don't fall straight in. Instead, they spin around it, faster and faster, like water swirling down a drain, but on a scale so massive it defies understanding. These pieces of cosmic debris accelerate to speeds approaching the speed of light. They crash into each other, they compress, the friction between them skyrockets, and the whole disk becomes a chaotic storm of motion and heat. The spin is so intense that the gas doesn't just glow, it becomes incandescent, shining brighter than a million suns packed together. And here comes the reveal. This is why the ring glows. The material spiraling inward rubs against itself with such incredible force that it heats up to millions of degrees. At those temperatures, it emits light across the entire electromagnetic spectrum. Visible light, X-rays, gamma rays. Even though the black hole remains perfectly dark at its center, the swirling ring around it becomes one of the brightest objects in the universe. This accretion disk is a cosmic furnace, a spinning ring of fire that marks the border between the universe we know and the unknown realm swallowed by the black hole. But the sight is not just beautiful, it's a warning. Because the closer we drift, the more intense the radiation becomes, the hotter the surroundings get, and the more distorted space appears. The ring is only the outer sign of the chaos happening deeper in. Just beyond this glowing storm lies the region where gravity becomes so overwhelming that nothing, no ship, no light, no hope can escape. And that brings us face to face with the next question pushing us forward into the heat. If this ring already burns with millions of degrees, what will happen to us as we move even closer to the black hole's blazing heart? Why is everything around us growing hotter, even though space itself is supposed to be freezing cold? Out here, far from any star, you'd expect temperatures to drop toward absolute zero. But as we drift closer to the black hole's glowing ring of fire, the opposite happens. Our sensors begin to spike, alarms flicker, and the hull of the spacecraft vibrates softly under the rising assault of energy. The surrounding darkness is no longer quiet or harmless. It feels charged, alive, boiling with invisible danger. Something out here is turning cold space into a furnace, and the question presses against our minds like heat against glass. What could possibly be causing this? The tension around this thickens with every second. Radiation floods the region, pouring off the accretion disk in waves so intense they could strip the atmosphere from a planet. The gas and dust spiraling inward aren't just glowing, they're blazing with unimaginable heat. They smash into each other at nearly the speed of light, generating X-rays and gamma rays that shoot out in every direction. Our ship's shielding groans as it absorbs the onslaught, the metal trembling with each spike. Outside, the disk roars silently, A storm of fire so bright that even through filtered displays, it looks like the universe is burning at its edges. We're close enough now that the radiation isn't just something we measure. It's something we feel in the rising pressure of the cabin, in the hum of overworked systems, in the sense that the very environment is turning hostile. And then comes the reveal. The heat and radiation aren't the only signs of the black hole's power. At its poles, something extraordinary happens. As the spiraling material in the accretion disk compresses and twists, magnetic fields snap and reconnect with explosive force. These tangled electromagnetic storms create towering jets, beams of pure energy that shoot out from the black hole's north and south poles at nearly the speed of light. They stretch for thousands of light years, carving through space like massive cosmic blowtorches. They're so bright that telescopes can see them from other galaxies. They carry particles accelerated to incredible energies, enough to outshine the entire accretion disk for brief moments. These are the black hole's warning flares, its way of announcing its presence to the universe even though the hole itself remains completely invisible. For the first time in our journey, space feels genuinely hostile. The heat is rising, the radiation is climbing, light is twisting into strange shapes, and the jets slicing through the darkness remind us that this environment is not meant for human bodies or fragile ships. We're brushing against the limits of what any craft can survive. And ahead of us lies something even more dangerous, even more final, even more impossible to escape. Because the next step isn't just another region of strange physics or intense gravity, it's a boundary that marks the line between return and oblivion. A line that no object has ever crossed and come back from. Which brings us to the question waiting like a silent wall at the threshold of the abyss. What happens when we approach the point of no return, the event horizon itself? What lies beyond a boundary with no escape? A line so absolute that not even light, the fastest thing in the universe, can cross it and return. As our spacecraft inches closer, the glowing accretion disk warps into impossible shapes, curving around the black hole like liquid fire smeared across a dark canvas. Ahead of us, the region where space seems to fold inward marks the most infamous frontier in the cosmos, the event horizon. It appears subtle at first, not a wall or a barrier, but a strange calm, a circular silhouette where the universe seems to vanish into itself. No flashes, no noise, no warning sign. Just a perfect border between the knowable and the unknowable. And yet, the question hangs heavy. What actually waits on the other side? The tension rises as the spacecraft's instruments scream in protest. Gravitational forces spike dramatically. Space around us begins to stretch in odd ways as if the universe is being pulled toward an invisible drain. The escape velocity, the speed needed to break free from gravity, rises higher and higher until it reaches an impossible value, the speed of light. At this boundary, even a photon, which naturally travels at that very speed, cannot make it out. If light can't escape, how could a spacecraft? The event horizon isn't just a region of strong gravity. It's a one-way membrane. Cross it, and every possible future leads deeper inward. Every path, every direction, every timeline flows toward the center. There is no turning around, no braking, no reversing engines powerful enough to pull away. The laws of physics themselves forbid escape. And now the reveal settles over us with chilling clarity. Crossing the event horizon means we can never return. Not ever. Now with infinite fuel, now with impossible technology, not even with the ability to travel faster than light. Once inside, escape doesn't simply become difficult, it becomes physically impossible. Space and time themselves rearrange so that all paths curve inward. The idea of a way from the black hole stops making sense. Even looking outward becomes meaningless because the outside universe grows dimmer, slower, more unreachable with every passing moment. This boundary is the ultimate cosmic trapdoor, and once you fall through, you belong to the black hole forever. But before we cross it, before we let ourselves slip into that irreversible darkness, there's one more question we need to answer. One more mystery about what the experience of falling actually feels like. The scientists speak of effects that distort time, stretch bodies, twist reality. They talk about things that sound like science fiction but are rooted in real physics, and we're about to experience every one of them firsthand. So as we float at the edge of the black hole shadow, staring into a darkness no human has ever entered,
we're left with one last burning question. What will it actually feel like when we fall into a black hole? When time, space, and our own senses begin to warp around us? Why does time seem to behave differently the moment we begin falling toward the black hole? Why does the universe itself feel like it's slowing down outside while everything inside the ship feels completely normal? As we pass the threshold of the event horizon, something subtle but profound begins to happen. Our clocks tick steadily, our hearts beat at their usual rhythm. Every second feels just like the last. Yet when we look outward, when we check our external monitors or try to observe the universe we came from, it's as if everything beyond the event horizon is drifting into slow motion. Stars appear to freeze. The light from the accretion disk seems to stretch into a sluggish glow. Even the radiation storms seem to crawl instead of flash. And the question presses against our minds like a growing weight. Why is time itself acting differently on the inside than it does on the outside? The tension deepens as our instruments confirm the impossible. The clocks on the ship continue ticking normally, second after second, but clocks trying to measure time outside start to fall out of sync. Messages we send outward trail off into stretched delays. Signals from the universe take longer to arrive. It's as though time outside has become thick and heavy, like syrup, slowing everything down. Nothing seems wrong with the ship, we still feel normal, but the universe beyond the event horizon becomes strangely still, like a pause frame in a movie. And if someone were watching us from outside, they'd see the opposite effect. To them, we'd appear to slow down, stretch out, freeze at the edge, not because we're stopping, but because gravity is twisting time itself. And now comes the reveal. This is time dilation, one of the strangest predictions of Einstein's theory of relativity, now unfolding right in front of us. Gravity doesn't just pull on matter, it pulls on time. The stronger the gravity, the slower time moves. Near a black hole, where gravity becomes nearly infinite, time stretches like elastic. Inside our ship, far from that gravitational horizon, time flows normally. But compared to the outside universe, we're drifting into a deeper, slower river of time. From our perspective, everything outside speeds up and races ahead. From their perspective, we're slowing down and fading away. Two realities, both true depending on where you stand. But the strange warping of time is only the beginning. The black hole doesn't just twist when things happen, it twists what happens to us. Gravity will begin pulling on our bodies in uneven ways, stretching us from toe to head, bending the very space we occupy. Time dilation affects how we perceive the universe, but the next effect changes something far more personal. What happens to the human body itself as we sink deeper into the black hole's gravity well? Why do objects, including our own bodies, begin to feel longer, thinner, and strangely pulled as we fall deeper toward the black hole center? At first, it's just a subtle sensation, almost like standing in a powerful elevator that's dropping too fast. Our feet feel slightly heavier, our heads slightly lighter. Nothing painful yet, nothing dramatic. But soon the pressure grows. The floor of the ship seems to tug downward with an invisible force, while our upper bodies feel like they're drifting upward. It's an eerie, uncomfortable pull, gentle, then stronger, then alarmingly intense. And the question rises with every passing second. Why does the black hole stretch us like this? The tension deepens as the invisible force becomes unmistakable. These are tidal forces, the same kind that cause ocean tides on Earth, but here multiplied by unimaginable gravity. The gravity near our feet is significantly stronger than the gravity near our head. Even though the distance is small, the difference in gravitational pull is enormous. It's as if space itself is grabbing us by the ankles and yanking with everything it has while barely tugging at our shoulders. Objects in the ship stretch. Loose items drift into strange, elongated shapes. Even the metal framework groans under uneven stress. The closer we fall, the more violent this stretching becomes. There's no gentle transition. Tidal forces rise steeply and relentlessly. Our bodies begin to lengthen in tiny, invisible increments. The atoms at our feet are pulled harder than those above. And then comes the reveal. This horrifying transformation has a name: spaghettification. It sounds almost comical, but the reality is anything but. Spaghettification is what happens when tidal forces stretch an object so violently that it becomes a long, thin strand. A spacecraft becomes a metal noodle. A human body becomes a fragile thread. Stretched until every molecule is torn apart, this is the ultimate fate for anything that ventures too close to a black hole center. Not crushed, not burned, stretched, pulled into a long filament of atoms before being swallowed forever. The process is silent, inevitable, and absolute. But we're not at the breaking point yet. We're still hovering in the region where spaghettification is just beginning to take effect, where the stretching is noticeable but not yet deadly. The deeper we go, the more powerful these forces will become, and soon there will be no structure, no metal, no bone, no cell that can withstand them. And beyond even that lies something stranger, a place where space and time twist so violently that the laws of physics as we know them fall apart. Which leads us to the next mystery waiting in the crushing darkness ahead. If this is what happens near the event horizon, what awaits us deeper, inside the black hole center itself? Why has the darkness ahead of us become absolute, so complete that not even the faintest glow, reflection, or shimmer can be seen? Up until now, even in the deepest parts of space, there was always some kind of light. Distant stars, glowing gas, scattered dust, the fiery swirl of the accretion disk. But now, as we move deeper, all of that disappears. The darkness becomes thick, heavy, almost physical, like a curtain has dropped over the universe. It feels unnatural. It feels wrong. This isn't night. This isn't shadow. This is a kind of darkness the human eye was never built to witness. A darkness that seems to swallow everything before it even reaches us. And the question presses against our minds like a cold hand. Why can't we see anything at all? The tension tightens as we realize what's truly happening. Light itself, the fastest traveler in the cosmos, is no longer able to reach us from the outside. Photons that would normally race through space at nearly 300,000 kilometers per second are being trapped, twisted, and pulled inward with us. There are no reflections, no scattered glimmers, no light bouncing off the ship's hull, nothing. Even the radiation that once blasted across our path has vanished. In this region, every photon that tries to escape is dragged back by gravity, locked into a swirling descent toward the center. If a star exploded 1,000,000 kilometers away, its light wouldn't reach us. If the brightest supernova erupted just outside, we would see absolutely nothing. We have entered a place where visibility itself has died. And then comes the reveal that seals our fate. We are now fully inside the event horizon. The boundary we crossed a moment ago wasn't just a line in space. It was a line between two completely different realities. Outside the event horizon, light can escape. Inside, it cannot. Outside, you can see the universe. Inside, the universe disappears. No matter how powerful a flashlight, how bright a beacon, how intense a laser, we will never see outward again. The path behind us is sealed, not by walls or force fields, but by the simple fact that space and time are now funneling everything inward. We're not just traveling forward, we're being carried forward, like leaves caught in a cosmic waterfall with no possibility of climbing back. And yet, inside this absolute blackness, there is something else, something deeper and far stranger. The laws of physics we've lived by our whole lives start to wobble, like a bridge swaying in a storm. Our instruments flicker with readings that contradict each other. Time behaves strangely. Space feels twisted. Directions lose meaning. Objects inside the ship drift as it's suspended in a place where up, down, and forward are no longer stable concepts. We stepped beyond the reach of normal physics into a region where even our most brilliant theories begin to crumble. And that leads us to the next haunting question waiting in the unseen depths. If this darkness marks the end of everything we understand, what happens now that the very laws of physics themselves are beginning to bend? Why don't the normal rules of reality apply anymore? Why do space, time, direction, and motion all feel like they're slipping out from under us as we fall deeper into the black hole? Inside the event horizon, our senses lose their anchors. The ship's navigation system spins uselessly, unable to decide what direction forward is. Distances stretch and shrink as if the very fabric of space is breathing. time refuses to behave, flickering between moments that feel too long and others that vanish before we can process them. Even gravity, the force that brought us here, no longer acts in a way we recognize. It doesn't simply pull, it distorts, folds, and twists everything around us, including our own perception. And the mystery grows heavier. What is happening to the universe in here? The tension worsens as our instruments begin to contradict each other. Some readings show space stretching infinitely in front of us. Others show it collapsing to a point. Our internal clocks tick steadily, but our external sensors register time behaving like a tangled thread. Looping, slowing, speeding, bending. It's as if we're drifting through a place where the universe's basic rules have been rewritten. The shapes of objects inside the ship waver, bending slightly at the edges. Shadows fall in directions that make no sense. There's no horizon, no reference point, no surface or skyline to hold on to. We're moving, but it doesn't feel like movement. We're falling, but not downward. We're drifting in a direction that might not even exist in the normal world. And now comes the reveal that seals our fate. Some theories suggest that inside a black hole, forward doesn't mean what it means outside. The structure of space-time is so warped that moving deeper inward may be the only possible direction. Every path curves toward the center. In a sense, falling is no longer a choice or even emotion. It becomes a destiny, a built-in future. According to general relativity, once inside the event horizon, the singularity isn't a location you move toward. It becomes a moment in time you move into, the way we move toward tomorrow. Just as you cannot choose to avoid the future, you cannot choose to avoid the singularity. Physics inside this realm suggests something unsettling. We may not be traveling through space anymore. We may be traveling through a distorted timeline that ends at the core.
And that realization leads us to the most haunting mystery of all, pulling at our minds like gravity pulling at our final molecules. If all paths in here lead to a single inevitable point, what exactly lies at the core, the singularity waiting at the center of the black hole? What exactly is a point with infinite density? A place where all the matter that once belonged to stars, planets, dust clouds, even light itself, is crushed into something smaller than the tip of a needle. As we sink deeper into the black hole, that question grows heavier than the gravity around us. There is no light here, no sound, no shape, just an overwhelming pull drawing us toward a destination we cannot see, cannot measure, cannot truly imagine. Every theory we've ever built begins to tremble under the weight of this mystery. Because what does it mean for something to have infinite density? What does it mean for space to collapse into a point? And what happens to everything that falls inside? These questions echo in our minds as we drift toward the unseen heart of the darkness. The tension intensifies as the gravity around us skyrockets. It doesn't grow gradually. It rises like a cliff face, an impossible incline that steepens with every fraction of a second. The tidal forces that once tugged at our bodies now pull so violently that the ship's reinforced frame begins to shudder. Space narrows. Time stretches. Our motion becomes more a surrender than a journey. Gravity here is no longer a force we fall through. It is a force that consumes the very meaning of distance. Even the idea of closer and farther begins to collapse. Space compresses. The coordinates that once described our location warp beyond recognition. Everything funnels inward, drawn toward a single point of unimaginable density. And now we reach the reveal. This point has a name, the singularity, the core of the black hole. It is where the laws of physics break down, where our formulas fail, where the universe stops obeying the rules we know. According to our best theories, the singularity is a place where matter is crushed infinitely small, where gravity becomes infinite, and where the curvature of space becomes so extreme that even the concept of location loses meaning. It is the ultimate endpoint of everything that crosses the event horizon, a cosmic full stop in the story of matter. And yet, even here, even at this theoretical limit, uncertainty reigns, because no one has ever observed the singularity directly, and no one knows if it truly exists the way our equations describe it. Which brings us to an unsettling possibility. What if the singularity isn't the end? What if the crushing point waiting ahead is not a final destination, but a doorway to something else? Something even stranger than the black hole itself? Could the singularity lead somewhere beyond our universe? Could the singularity, the point of infinite density crushing everything to nothing, actually lead somewhere else? It sounds impossible, unreal, like science fiction stretching far beyond the edges of reason. But as we drift closer to that mysterious heart, a strange question has followed scientists for decades. What if the singularity isn't a dead end at all, but a hidden gateway? A doorway that doesn't just destroy matter, but sends it somewhere unexpected. Somewhere outside our universe, or perhaps into another one entirely? The tension rises as we explore the most daring ideas in modern physics. Some theories suggest that the intense warping of space and time inside a black hole might create tunnels, paths that twist space-time so dramatically that distant regions of the universe touch. These hypothetical structures are called wormholes. Imagine folding a massive sheet of paper so two far apart points suddenly meet. A wormhole is that concept applied to the universe itself. In these theories, the singularity could be the thrashing, violent center of such a tunnel, an opening on one end that leads to another point far across space, or even a completely different universe entirely. These ideas are bold, strange, and stretch scientific imagination to its very limits. They offer the possibility that falling into a black hole isn't simply destruction, it's transition. But now comes the reveal. As incredible as these concepts are, there remain mathematical possibilities, not proven realities. The equations of general relativity suggest that wormholes can exist, but the same equations also show they might collapse instantly, sealing before anything can pass through. We have no evidence that any wormhole has ever formed naturally, stayed stable, or connected two places successfully. And while the singularity might mathematically resemble the mouth of such a tunnel, nature often behaves differently from equations. So as beautiful, bold, and mind-bending as these theories are, they remain untested ideas, glimpses of what might be possible in the deepest parts of space-time. Still, the thought lingers in the darkness around us. If the singularity is more than just a crushing endpoint, if it's even remotely connected to something like a wormhole, then perhaps the black hole's center isn't simply where things end, but where reality itself could reshape. Which brings us naturally to the next astonishing question. If wormholes really can exist, where would they lead, and how would they bend space to make that possible? If wormholes exist, real tunnels carved into the structure of space-time, then where do they lead? This question echoes through the dark as we drift deeper toward the black hole center, because if a wormhole is hidden inside, the possibilities are almost unbelievable. Could it open somewhere across our galaxy? Somewhere on the opposite side of the universe? Or somewhere even stranger? Maybe into a different universe altogether? The idea is both thrilling and terrifying. A cosmic shortcut through reality itself, created by the same gravity that crushes everything falling inward. The tension builds as we imagine how a wormhole would actually work. Space isn't just emptiness, it's a fabric, a three-dimensional surface that can bend and stretch. If you picture the universe like a giant cosmic sheet, then a wormhole is what happens when that sheet folds, causing two faraway points to touch. Instead of traveling the long path across the surface, you slip through the fold, falling from one side to the other in an instant. The distance that might normally take millions of years to cross could shrink to a moment. Light years could collapse into heartbeats. You wouldn't just travel through space, you'd travel under it, around it, through it, in ways we can barely imagine. It's the universe forming a tunnel, a secret passage connecting places that would normally be impossibly far apart. And here comes the reveal. If such wormholes are real, they could connect different regions of the same universe, or possibly even different universes entirely. Some theories suggest that every black hole might be connected to a distant white hole, with matter entering one side and blasting out the other.
Others propose that wormholes could link alternate versions of the cosmos, parallel realities branching from our own. In this picture, the singularity might not be an end, but a doorway, opening into places beyond our cosmic horizon. It's a concept so bold and so vast that it completely challenges how we think about space, distance, and the very structure of existence. But this leads to an even more precarious question, because even if wormholes do form inside black holes, even if they truly connect these impossible distances, there's still one major problem scientists keep returning to. How stable are they? Why do wormholes collapse almost instantly? Why can't these cosmic tunnels stay open long enough for anything to travel through them? As we imagine drifting toward a black hole's hidden core, the promise of a wormhole feels almost within reach, a bridge, a shortcut, an escape from the crushing gravity pulling us inward. But the deeper we go, the more a single troubling question grows. If wormholes can form, why don't they last? Why do they slam shut faster than the blink of an eye, trapping anything inside or destroying the tunnel entirely? The tension rises as we learn the brutal truth. The gravitational pressure inside and around a black hole is so overwhelming that any tunnel linking 2 points in spacetime gets squeezed, twisted, and crushed with unimaginable force. A wormhole isn't a stable structure, it's a delicate crease in the fabric of reality. And black holes don't just bend that fabric, they tear it, stretch it, and slam it inward with unstoppable intensity. As soon as a wormhole begins to open, the walls collapse inward faster than any object could hope to pass through. The tunnel pinches shut instantly, like a rubber sheet snapping back the moment you try to poke a hole through it. The gravity's too strong, the pressure's too extreme. The universe simply refuses to hold that tunnel open. And now the reveal. Scientists have proposed that the only way to keep a wormhole stable, open long enough for something to actually pass through, would be to fill it with exotic matter. This isn't matter as we know it. It's hypothetical material that has negative energy or negative pressure, something completely unlike anything we've ever touched or observed. Exotic matter, if it exists, could push outward against the crushing gravitational forces holding the tunnel's walls open like invisible braces. Without it, the tunnel collapses instantly. With it, a wormhole might stay open long enough for light or even a spacecraft to pass through. But since exotic matter has never been found, wormholes remain beautiful mathematical solutions that may never be physical realities. Still, even though wormholes seem unstable and impractical, the idea leads us to another strange possibility, another theoretical cosmic object that sits on the opposite side of a black hole's behavior. Something that doesn't suck matter inward, but explodes it outward. Something that functions like a time-reversed black hole. Which leads us to our next question. Could such an object exist? An object that only pushes matter out and never lets anything fall in? What kind of cosmic object would behave in the strangest way imaginable? One that only pushes matter out and never lets anything fall in? As we sink deeper toward the black hole's center, surrounded by ideas of wormholes and tunnels through space-time, another mystery rises from the theoretical shadows. What if there exists an object that is the exact opposite of a black hole? Something that doesn't swallow everything around it, but instead blasts matter outward with unstoppable force. A place where gravity doesn't trap you in, it ejects you before you can get close. The tension sharpens as we imagine how such an object would behave. A white hole, if it exists, would be a cosmic fountain. Nothing could enter it. Not light, not matter, not even the strongest gravitational pull. Anything approaching would be repelled instantly, thrown backward with unimaginable energy. It would appear blindingly bright because all the matter it expels would heat up, radiating intensely as it's forced outward. But unlike a star or a supernova, a white hole would not allow anything to stick, fall inward, or even skim its boundary. Space around it would be chaotic, filled with material blasting out in every direction. And while a black hole hides behind an event horizon you can cross only once, a white hole would stand behind an event horizon you can never reach. It's the ultimate no-entry zone. And now comes the reveal. A white hole is essentially a time-reversed black hole. In a black hole, time flows inward, pulling matter deeper, never allowing escape. In a white hole, time would flow outward, preventing anything from ever entering. In the mathematics of general relativity, this reversal works beautifully. If you flip the direction of time in the equations for a black hole, you get a white hole. The math doesn't reject it. The equations don't break. They simply describe a mirror image object that shoots matter out the way a black hole pulls it in. It's a perfect theoretical twin, a cosmic opposite, with its own form of event horizon and its own strange rules. But here's the part that pulls us toward our next big question. Does anything in the real universe actually behave like this? Despite decades of searching, astronomers have never confirmed a single white hole. There are strange explosions, sudden bursts of energy, and mysterious cosmic flashes, but none match the exact behavior a white hole would need to show. Some scientists believe they may form briefly and then vanish instantly. Others think they might not exist at all. And some propose that a white hole might actually be what a black hole becomes at the very end of its life. Which brings us to the next mystery, rising like a flare in the darkness. Have we ever seen anything that could be a real white hole? Have we ever actually spotted a white hole? One of those theoretical cosmic fountains that could blast matter outward, but never let anything in? Astronomers have scanned the sky for decades, hunting for any sign that such objects might exist. They search for clues in gamma ray bursts, in sudden cosmic flares, in strange flashes of radiation that appear without warning and disappear just as quickly. Every time something unpredictable erupts in the sky, the same question whispers through the scientific community. Could this be a white hole? Yet none of these events have matched the exact signature a true white hole would need to show. The mystery lingers, taunting us with possibilities. The tension sharpens when we examine the universe's most violent explosions. Some gamma ray bursts last only a fraction of a second, too short to be linked to supernova, too intense to be ordinary star collapses. Some strange eruptions seem to appear out of nowhere, in regions with no stars, no galaxies, no obvious source. These sudden flashes make scientists pause. They consider everything: colliding neutron stars, magnetic storms, primordial echoes from the early universe. And in the back of their minds, quietly, the idea of a white hole surfaces. Could these brief flashes be a white hole opening, spitting out matter, then collapsing instantly? Could we be catching a glimpse of the theoretical becoming real? But here's the part that pulls us toward our next big question. Most experts doubt white holes truly exist. The primary reason is simple: physics fights against them. To keep a white hole stable, space-time will need to run backward locally, and the conditions required to produce one aren't seen anywhere in the universe. There's no known process that can form a white hole naturally. Wormholes aren't stable. Exotic matter hasn't been found, and the math that describes white holes, though elegant, doesn't match what we actually observe in space. White holes remain beautiful on paper, but fragile in reality, likely collapsing instantly or never forming at all. Every strange cosmic flash observed so far has eventually been explained by more ordinary, though still dramatic, astronomical events. And yet, in the shadow of this uncertainty, our journey continues deeper into the black hole. Even if white holes don't exist, the idea raises a chilling possibility for us. Because if there is no opposite to a black hole, no escape, no outflow, no hidden exit, then the outcome of our fall becomes all the clearer, all the more final. Which brings us to a far more personal and unsettling question. What if we can never escape the inside of this black hole? What does forever mean when you're trapped within its gravity? What does forever truly mean once you're trapped inside a black hole, when every direction, every future, every possible outcome leads to the same place? Out in normal space, forever is just a word, an idea we use for things that last longer than a human life. But in here, inside the event horizon, forever becomes something far more literal and far more terrifying. There is no turning back, no stopping, no drifting sideways into safety. Time itself has changed shape. Instead of flowing freely in all directions, it now flows only one way, downward, inward, straight toward the core. And the deeper we fall, the more the question grows inside us like a cold shadow. What does it mean to be trapped in a place where the future has only one destination? The tension thickens as we begin to understand how time behaves differently here. It doesn't feel like normal motion. We're not moving toward the singularity in the same way a ship moves through space. Instead, time itself is dragging us there. It's like standing in a river whose current grows stronger with every second. You can try to swim sideways, but the water keeps pulling you downstream. Try to go back, and the current becomes even stronger. Eventually, the flow becomes so powerful that resisting it isn't just difficult, it's impossible. Inside a black hole, the flow of time behaves the same way. The singularity is not just the location we approach. It becomes our future, the moment we are pulled toward just as surely as the next second on a clock. The closer we drift, the more this flow accelerates, making the pull feel inevitable, unstoppable, built into the very structure of the universe. And then comes the reveal. Reaching the center of a black hole isn't just likely, it's guaranteed. Once inside the event horizon, every path you could take leads directly into the singularity. Even if you could turn your engines to their maximum, even if you had infinite fuel or impossible technology, nothing would change. The singularity is woven into the fabric of time itself inside this region. Avoiding it would be like trying not to experience tomorrow. It isn't a matter of where you go, it's a matter of when you inevitably arrive. The one future available to us ends at that point of infinite density, a place where the laws of physics collapse into pure mystery. And this inevitability raises a haunting idea. If we are doomed to reach the center, then so is everything else that falls in. Every star, every dust grain, every photon, every planet, every bit of matter that has ever crossed the event horizon. Which leads to the deeper question that physicists have been arguing about for decades, a question that goes beyond survival or destruction and strikes at the heart of the universe's rules. If everything inside a black hole must end at the singularity, then what happens to all the information carried by that matter? Where does it go? Does it simply vanish? Or is something stranger happening? Does information actually disappear inside a black hole, vanish completely, as if it never existed? This question isn't just a curiosity, it's one of the most unsettling mysteries in modern physics. Every particle, every atom, every bit of matter carries information about its structure, its history, its interactions. In the normal universe, this information can change forms, scatter, transform, but it can never be fully destroyed. That rule is written deep into the foundations of quantum physics. But inside a black hole, something strange happens. Everything that falls in seems to be erased at the singularity. All structure, all detail, all information is crushed out of existence. And so the question looms in the dark around us. Does the universe really allow information to be destroyed? The tension tightens because if information does vanish, it breaks one of the most fundamental laws of physics, the conservation of information. Quantum mechanics insists that information about a physical system must always be preserved. Nothing can simply disappear. No atom's history, no particle's path, no detail of how matter came to be what it is. If black holes truly delete information, then quantum mechanics fails. But if quantum mechanics is right, then black holes must somehow preserve information, even though everything falling into them appears to be crushed to nothing. Both ideas cannot be true at the same time, and this contradiction has plagued physicists for decades. It's a paradox at the heart of reality. The black hole swallows matter, but what happens to the information encoded in that matter? And finally comes the reveal. One of the most intriguing solutions is that the information might not disappear inside the singularity at all. It might be stored on the surface of the black hole, at the event horizon itself. The idea is that the event horizon acts like a cosmic memory layer, a thin shell holding all the information about everything that has ever fallen inside. It doesn't describe the matter in its original form, but it preserves the essential data encoded in patterns of light, particles, and quantum states. Instead of vanishing into the singularity, the information becomes smeared across the two-dimensional surface of the event horizon like a hologram, storing the details of a three-dimensional world. This concept is known as the holographic principle, and it radically reimagines what a black hole really is, not just a pit of destruction, but a strange kind of storage device written in warped space-time. But this idea only gained traction because of a bold and groundbreaking prediction made by one of the most famous physicists in history, Stephen Hawking. His work suggested that black holes are not completely black. They slowly emit energy over time, a process that might carry information back out into the universe. Which brings us to the next mystery, waiting in the dark. What exactly is Hawking's strange prediction, and how can a black hole slowly evaporate? How can something as powerful and unstoppable as a black hole, an object that swallows stars, light, and entire planets, slowly evaporate over time? At first, the idea sounds impossible. Black holes are supposed to be the ultimate traps, the deepest sinks in the universe. Nothing escapes them. Nothing leaks out. Nothing returns once it crosses the event horizon. And yet, in the quiet darkness around us, a strange question rises. How can something that only takes eventually begin to give? This mystery puzzled scientists for decades, until one idea changed everything. The tension builds as we drift near the edge of the event horizon, the place where space-time stretches so violently that even empty space isn't truly empty anymore. In the quantum world, empty space constantly flickers with pairs of tiny particles appearing and disappearing. Particles and antiparticles popping into existence and vanishing again almost instantly. Normally, these pairs collide and cancel each other out, blinking in and out of reality like sparks. But near a black hole's horizon, something extraordinary happens. The intense gravitational pull can separate these pairs before they collide. One particle falls into the black hole while the other escapes into space. To an outside observer, it looks like the black hole is giving off a faint glow, a tiny trickle of energy leaking from its edges. And then comes the reveal. This glow is Hawking radiation, named after Stephen Hawking, who predicted it in 1974. According to his theory, when particles escape the event horizon, the black hole loses a tiny bit of mass. Over enormous spans of time, this process causes a black hole to slowly shrink, losing mass and energy bit by bit. The larger the black hole, the slower it evaporates. But even the biggest ones are not eternal. They quietly emit these ghostly particles, gradually fading away. Eventually, after trillions upon trillions of years, the black hole becomes incredibly small, incredibly hot, and incredibly unstable. Its final moments end in a brilliant burst of radiation, a last flash of energy before it disappears entirely. But that final flash raises a deeper, more haunting question. If a black hole can evaporate, and if information somehow lives in its radiation, then what becomes of it all at the very end? What happens in those last explosive seconds when the black hole finally dies? What does a universe witness when a black hole reaches its final moment? What truly happens at the very end of a black hole's life, when something that once swallowed entire suns is reduced to something smaller than an atom? For billions, even trillions of years, a black hole sits quietly in the universe, slowly evaporating through Hawking radiation. Most of that time, it barely changes. But as its mass drains away grain by grain, its temperature begins to rise. Its radiation intensifies. Its edges ripple with quantum energy. And finally, when the black hole becomes tiny, far smaller than any star, planet, or even molecule, one last mystery emerges. What does the universe see during a black hole's final heartbeat? The tension grows as we imagine the dying moments of this cosmic giant. As the black hole shrinks, Hawking radiation doesn't weaken, it surges. The smaller the black hole becomes, the faster it evaporates. The faster it evaporates, the hotter it gets. Temperatures climb to staggering levels, far hotter than any star has ever been. The event horizon shrinks rapidly, collapsing at an accelerating pace. Space-time around it warps and ripples with violent fluctuations. Radiation pours out in a furious cascade, brighter and hotter every instant. Inside the dying black hole, whatever remains of matter and information is compressed into an ever tighter space. Every second that passes multiplies the energy trapped inside, building pressure like a cosmic spring, winding tighter and tighter. And then comes the reveal. The black hole ends not with silence, but with a final burst of radiation, a brilliant flash of energy that erupts into space as the black hole fully evaporates. This last explosion, often called the black hole death flash, releases all the remaining energy in one brief, powerful moment. It's not like a supernova, which blows apart a star's outer layers. This is pure radiation, a blinding burst of photons and particles that marks the disappearance of the black hole itself. After this flash, nothing is left. No core, no remnant, no shadow in space-time. The black hole is simply gone. But this final burst leaves behind a profound possibility, one that shakes the foundations of physics. If information is encoded in Hawking radiation, as some theories suggest, then perhaps this final explosion doesn't just end the black hole. It may scatter the hidden information back into the universe. The black hole that once consumed everything might in its last moment reveal traces of what it swallowed. Not in recognizable form, not as planets or stars, but in the faint quantum patterns of the radiation it releases. And that leads us straight to the next big question, rising like a spark from the ashes of that final flash. If black holes die and release information back into the universe, then how much do we really understand about them at all? How much do we really know about black holes, these silent giants lurking in the dark, swallowing light, bending time, and challenging every rule we thought the universe followed? After witnessing their power, their strange effects, their mysterious deaths, a new question rises. Are we truly beginning to understand black holes, or are we only scratching the surface of something far deeper? For every answer science has uncovered, a dozen new mysteries appear, stretching out ahead of us like an endless cosmic maze. The tension builds as we consider the biggest unanswered questions still drifting in the dark. We still don't fully understand what happens inside the event horizon. We don't know if the singularity is a real physical point or a sign that our theories need to be rewritten. We don't know whether wormholes can actually form or if exotic matter capable of stabilizing them exists. We don't know if information is truly preserved on the event horizon or encoded in Hawking radiation. We don't know whether white holes exist, whether time can flow backward in special regions of space-time, or whether black holes can connect distant parts of the cosmos. We don't know how quantum mechanics and gravity fit together inside a black hole, or whether new physics, deeper, stranger, more fundamental, is waiting hidden in the core. And perhaps the simplest yet most haunting question remains. What happens beyond the final limits of our understanding, in places where space and time collapse into something entirely new? And then comes the reveal. Every discovery we make about black holes transforms our understanding of the entire universe. When Einstein predicted them, even he didn't believe they would be real. Then we found the first ones. Then we learned they power some of the brightest objects in the universe. Then Hawking revealed that they could evaporate. Later quantum theory suggested they store information. And now observations of merging black holes are giving us gravitational waves, ripples in space-time itself, letting us listen to the universe in a brand new way. With each step forward, black holes reshape our understanding of physics, forcing us to rethink space, time, energy, and even reality. They aren't just strange objects, they're the key to questions that could rewrite the laws of nature. But the most surprising twist of all is this. Black holes aren't simply isolated monsters lurking in the dark. They aren't solitary destroyers. In fact, they play a much larger role, one that affects entire galaxies, including our own. They help sculpt the structure of the cosmos. They influence the motion of stars. They shape the evolution of galaxies. They act almost like cosmic engines, quietly steering the universe on a grand scale. Which leads us to the next fascinating question, pulling us deeper into the story. What sits at the center of our own galaxy, and how does a black hole shape the Milky Way itself? Why do entire galaxies, massive systems made of billions of stars, spin the way they do, as if held together by an invisible engine deep at their centers? When we look at the Milky Way from afar, it appears to swirl like a cosmic whirlpool, its spiral arms stretched out for tens of thousands of light years. But something powerful must be anchoring that motion. Something so massive that it keeps stars orbiting at incredible speeds without flying off into space. And that raises a profound question. What exactly sits at the heart of our galaxy, controlling the dance of suns, planets, and cosmic dust all around it? The tension builds as we examine the motions of stars near the galactic center. These stars aren't drifting gently like the ones in our part of the Milky Way. They're whipping around at astonishing speeds. Some race in tight loops, others slingshot around invisible corners, all of them pulled by a gravitational force stronger than anything else nearby. Whatever's influencing them must be compact. It must be heavy, extremely heavy. In fact, the only way to explain the motions of these stars is to assume that they're orbiting a single object with unimaginable mass. Not a cluster of stars, not a giant planet, not a cloud of dark matter. Something far more extreme and far more dense. And now comes the reveal. At the center of the Milky Way lies Sagittarius A, a supermassive black hole about 4 million times the mass of our Sun. It sits in the dark, completely invisible, surrounded by swirling stars that orbit it like tiny sparks circling a silent cosmic anchor. We can't see the black hole itself, but we can see everything it affects. The stars racing around it, the gas heating near it, the gravitational grip it maintains over the galaxy. Sagittarius A is the Milky Way's central powerhouse, shaping the structure and behavior of our entire star system. Without it, our galaxy wouldn't spin the way it does. Its presence has held the spiral together for billions of years. But this revelation raises an even bigger question, one that doesn't just apply to the Milky Way, but to countless galaxies across the universe. What role do black holes play in shaping the cosmos itself, and could they be the engines behind the formation of galaxies? Could black holes, the very objects that swallow light and crush matter, actually help create galaxies? It sounds backwards at first. How could something known for destroying stars also help build the grandest structures in the universe? But as we drift through the Milky Way central region, watching stars orbit Sagittarius A, a new idea rises from the darkness. What if black holes aren't just monsters, but cosmic engines that shape the universe itself? The tension builds as we consider the power supermassive black holes unleash. When enormous amounts of gas fall towards black holes don't quietly consume it. Instead, some of that material gets trapped in swirling magnetic fields and blasted outward in gigantic jets, narrow beams of radiation and particles that shoot across space at nearly the speed of light. These jets can stretch for thousands of light years, carving through interstellar clouds, clearing out huge regions, and triggering the birth of new stars by compressing gas in distant regions of the galaxy. They can heat up entire galactic cores, influence how fast stars form, and even change the chemical makeup of star-forming clouds. Far from being silent destroyers, black holes can sculpt the space around them like cosmic blowtorches. And now the reveal. Supermassive black holes act as powerful cosmic architects. Their gravity organizes the motion of stars. Their jets reshape the interstellar medium. Their energy output influences when galaxies grow and when they stop growing. Many astronomers now believe that without a black hole at the center, galaxies might not form stable structures at all. In other words, black holes aren't just the result of galaxies, they might be one of the reasons galaxies exist in the first place. They stabilize, regulate, and energize the universe on a scale we're only beginning to understand. But after this long journey, past stars, through warped space, into the event horizon, and even down to the singularity, we're left with one final question, a reflection not about physics or mystery, but about perspective. After everything we've seen, everything we've imagined, what would it truly feel like to take this journey for real, and what does it reveal about our place in the universe? What would it truly feel like to make the journey we've just imagined, to leave Earth behind, drift past swirling stars, cross the event horizon, and plunge into the deepest darkness the universe has ever created? It's a question that lingers after everything we've seen, a question that reaches beyond science and touches something personal. Because even though this journey was guided by physics and theory, the emotions tied to it are very human. Curiosity, fear, awe, a longing to understand what lies beyond the edges of our world. And so the final mystery rises. If we could experience all of this for real, what would it mean to us? The tension builds as we look back on the path we took. We saw Earth shrink into a glowing marble, leaving behind the comfort of home for the absolute silence of space. We drifted through starfields, each one a burning giant hiding secrets of its own. We searched for an invisible monster using the strange dance of nearby stars. We watched the sun get torn apart, stretched into glowing threads. We navigated through twisted light, scorching radiation, and the swirling fury of the accretion disk. We crossed the event horizon, the point of no return, where time bent, space warped, and the universe itself fell apart. We faced the singularity, the ultimate unknown. We dared to explore wormholes, white holes, jets that shape galaxies, and the possibility that black holes might be the architects of the cosmos. Every step was filled with danger, beauty, and mysteries so large they made us feel small. Yet every moment also revealed something bigger than fear, a sense of wonder at how strange and powerful the universe truly is. And now the reveal. While we may never travel into a black hole, no human ship, no body, no technology could survive such a journey. The ideas behind this adventure guide our deepest search for truth. Black holes challenge the limits of physics, push our theories to the breaking point, and demand that we rethink what space, time, and reality really are. They show us how much we still have to learn. They remind us that the universe is far more complex, far more mysterious, and far more beautiful than anything we experience in everyday life. This imaginary journey wasn't just a dive into darkness. It was a dive into the future of science, a glimpse at the questions that will shape the next century of discovery. But now that we've fallen into the deepest mystery the universe holds, a new question rises, one even bigger, older, and more profound than black holes themselves. Where did the universe come from? What was the moment of creation like? What is the mystery behind the birth of everything we know? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.